Okay, coming next, we have an asymptotic combinatorics and analytic combinatorics in several variables doubleheader, also a University of Waterloo doubleheader. So our next speaker is Andrew Luo from University of Waterloo, and he'll be speaking about automatically computing asymptotics of sequences with multivariate rational generating functions.
Can everyone hear me? Okay. Whoops. Yeah. So today I'll be talking about how you can automatically compute the asymptotic behavior of sequences when they have multivariate rational generating functions. I think I might have broken a record for like longest name for a talk at this conference. But anyways, yeah. So starting with some good news, the definition of a generating function hasn't changed over the last 10 minutes. So as usual, we're concerned with, so we have a sequence and we're representing it as the coefficients of a power series. So everyone's favorite example is the Fibonacci sequence. You can represent this either just as an infinite series, or you can rewrite it as a rational function. We're going to be looking more in the second case because it turns out that there's nice analytic analysis that you can do with this. So the main result that we use in analytic combinatorics is the Cauchy integral formula for coefficients. The idea is that if you take a generating function and divide it by so f of z, you divide it by z to the n plus 1, then the residue of that ends up just being the coefficient of the x to the n term. So you can use that to extract the n term of the sequence so going back to our Fibonacci example. So I need to mention that you have to integrate over a curve where f is analytic. Analytic around the origin. So going back to our Fibonacci example, if you choose your curve to be a circle of radius less than the radius of convergence of f, then you get this formula for the nth Fibonacci number. And then you can deform the curve of integration as long as you're not crossing any singularities. In fact, you can even go sort of beyond the two poles of the function, again, as long as you don't none of the curve doesn't cross it at any point. And then if you imagine, these two parts sort of coming together, you end up with this one large circle. And then two smaller circles going the other way. So the two smaller circles are going to be residues at these two poles. And then the larger circle is sort of like an error bound. And in this case, since there's only two poles, the circle we can deform all the way out to infinity, and then we show that this is actually equal to 0, which means that you can compute. You can get the sequence by just computing a residue, and then you get this the formula 1 over root 5 times. So here I forgot to mention phi is the golden ratio, but yeah. And also one thing to note is that if you just care about the dominant asymptotics, then that's given by this phi to the n. And this corresponds to the C2 circle, the C2 residue, which is the pole that's closest to the origin. And this will be important later on. But we're more interested in looking at multivariate generating functions. So now, just as the name suggests, we're considering multiple variables, and the main difference between the main challenge with a multivariate generating function is that your singular points are no longer isolated; they are defined by an algebraic variety. So you have infinitely many singularities, basically, but that sort of makes sense because there's also sort of infinitely many ways that you can compute asymptotics. So what we do is we define we go in a certain direction. So we have a vector r, and then we're looking at coefficients that are multiples of this vector. So example, if you have a bivariate generating function, then the all ones diagonal is just all the terms that are indexed by some multiple of the 1, 1 vector. So here you have like 0, 0, 1, 1, 2, 2, 3, 3, and so on and so forth. Okay, so to sort of motivate why we care about multivariate generating functions, I mean, we saw some examples of those from previous talks, but just to recap, we might want to, sorry, we might want to track multiple parameters. So this example I will cover again later on in the talk, but maybe you want to count the number of ways that you can tile, you want to tile a grid with cells, but you want to like, instead of just like restricting the number of cells that you use, you also want to restrict the number of rows. In order to do both simultaneously, you would need a bivariate generating function, and then you would look at the terms indexed by these two parameters. And then another reason is that sometimes it's actually easier to look at the multivariate generating function versus their univariate analog, even if it's just like a one-dimensional sequence. So a famous example of that is lattice path, restricted lattice path models. So I'll go over this in more detail in the next slide. So let's say you wanted to count the number of ways, the number of lattice paths of length n that you can do that goes in the following three directions. So you can go up, down and to the left, or down and to the right. So an example of that is given here. And you want to do it in a way that you stay in the positive, in the non-negative quadrant. So traditionally, how this was done is using the univariate generating function, which it was shown, or it was actually first guessed, but then later on proved to be true, that it satisfies a really complicated or a differential equation. And then if you try to do analysis on this differential equation, you can see that the asymptotics are given by some constant times 3 to the n, which is the exponential growth, and then multiplied by some other terms with a big O bound. But if you try to actually compute this constant from the different differential equations, you get that it's equal to 0.000000, so on and so forth. And they weren't able to like determine whether or not C was exactly equal to 0. And this remained open for like the next 7 years. So instead of continuing with this method, we turn to this trivariate generating function, whose all ones diagonal actually enumerates the exact same sequence. And so then you might be wondering, like, how is this easier to analyze than the univariate generating function? Well, for one thing, we can just have a computer program do it for us. So we have a Sage package that if you give it a generating function and then you ask it to compute the diagonal, it will do so for you. And in this case, it gives you this big O bound, which is stored as an algebraic number in Sage. So then this shows that, in fact, indeed, the sequence is big O of 2 root 2 to the n. So going back here, that also proves that this constant C is 0. But maybe we want better than a big O bound. Like we want to know actually like what the sequence is. Well, we can just ask the program to increase the precision. So here we have this expansion precision is equal to 2, which will compute up to 2 orders of precision. And then now it gives us, we have an actual like nice closed formula for the dominant asymptotics of the sequence. So before we go over more examples, just a quick recap of the theory behind how all of this works. It's similar to the univariate case. We have like a multivariate analog of the Cauchy integral formula, where now instead of integrating over a circle around the origin, we're integrating over a product of circles in each coordinate axis. And one thing to note here is that this integrand, the only place where the n appears is in the denominator of the z to the nr over here. And so it turns out that this integrand has the maximum modulus when the z to the r is minimized. So for computational and geometric reasons, we take the log of this and we get something called a height function here. So then we want to minimize the height function, which is equivalent, or not equivalent, but the minimizers of the height functions can be obtained by looking at the critical points along the singular variety of our generating function. Now, when the singular variety v of h is smooth, then it turns out that we can obtain these candidates for critical points just comes from this system of equations, which we can solve because they're all polynomials. And but critical points are not necessarily points that contribute to asymptotics. We also want because they may not necessarily be minimizers. So what we actually want are the minimal critical points. And here we define minimal to be a point such that no other point on the variety has coordinate-wise smaller modulus. In general, testing minimality is really difficult. You need to potentially use techniques from like real algebraic geometry, which is most of the time like computationally prohibitive. But there is one assumption we can make that makes this computation a lot easier, which is we assume that our generating function is combinatorial. Basically, it's meaning that it's eventually going to be non-negative, which for most, like if you're doing like combinatorics, most of the time you're going to get a combinatorial generating function because you can't get a negative number of things. And combinatorial functions have a nice test for minimality, which is that first of all, you have a guarantee that you have a minimal critical point in the positive real orthant. And then you can test for minimality then by just drawing a line from a candidate point to the origin and seeing if it crosses any other point in the positive real orthant and of your variety. And if it doesn't, then it will be a minimal point. Okay, so let's so the critical point equations I introduced earlier were assuming that our variety is smooth.
Why did you put the word easy in quotation marks on the previous slide? I mean, is there some counterpoint to that? Is it not so easy?
Well, like you still have to compute it, right? It's like it's easy to characterize, I guess, is what I mean by easy. Like you could still end up with a really complicated system of equations when you try to work with this. Okay, so what about if our what if our singular variety is non-smooth? Well, then we have to do this additional step where we want to decompose it into smooth components. So that raises the question of like how can we do that? Because like for example, if you had two curves coming together, one way you can decompose it is as like one of the curves and then union the other curve with this intersection point removed. But another way you can do this is you take the entire curve and just remove this intersection point where the non-smoothness happens and then make it its own component. And a spoiler alert, the first one is not great. And part of the reason is because if you were to look at the first component, it sort of misleads you into thinking that it's everywhere smooth. But if you look at the global picture, that's not the case because it actually intersects something. So we actually would want the second one in this case. And there's a nice general characterization for how we want to decompose these types of non-smooth varieties, which is something called a Winnie stratification, where basically you decompose it into components of decreasing dimension, such that if you take any component and then remove any component and you remove all the lower dimensional components, you get a smooth manifold that preserves certain local geometric properties. So as I mentioned, the first example here is not a Winnie stratification. The second one is, and just to show that Winnie stratifications are not generally like immediately obvious, a famous example is the Winnie cusp. So here, if you look at this variety, it's smooth everywhere except along this x-axis here. So if you just remove the x-axis, then you would get a line which is everywhere smooth, except that you can't just make that its own component and call it a day. You would have to, because if you look at the original picture, this the origin actually behaves very differently than the rest of the x-axis. So you would actually need to put it in its own component. There is an algorithm that was developed pretty recently in 2022 by Helmer and Anna that computes a Winnie stratification, and we do also have an implementation of this in Sage. Okay, so once you have your Winnie stratification, then you want to compute the critical points on each stratum. And it's the same idea as before, except that now your variety is defined by multiple equations, not just a single polynomial. So you want to look at the vanishing of the vanishing of the maximal minors of this following matrix. One thing to note is that this will still have the points of any substratum, so any lower dimensional stratum, will trivially still satisfy this set of equations. So one way you can get rid of them is by taking an ideal saturation, or you can use other methods like maybe an equidimensional decomposition to then clear out these extraneous solutions. But there is one special case where we don't actually need to do any of that, which is when we have something called a transverse factorization. So H has a transverse factorization if we can factor it in such a way that whenever any of the factors simultaneously vanish, they will have linearly independent gradients. And when you have a transverse factorization, then you also have an additional test for which of the critical points actually contribute to asymptotics, which comes from looking at these like log normal cones, which I will not go into too much detail here, but yeah. Okay, so now let's say once you've determined the points that contribute to asymptotics, it's just a matter of evaluating the multivariate Cauchy integral that I had before. There's two main steps to doing so. One is to deform your domain of integration close to the contributing points and then compute a residue. And then you do a polar change of coordinates to then get a Fourier-Laplace integral, which you can then get an asymptotic expansion of. I'll spare you the details of this computation because it's very technical, but I will introduce some quantities that do appear in the final asymptotic formula. So one is this log normal matrix. And then the second comes from when you turn it into this Fourier-Laplace integral, you end up with this function in the exponent, which you need to compute the Hessian of. It turns out to be extremely annoying, but still doable. And then once you put everything together, you get this following. This is the main theorem for transverse multiple points, which lets you basically get the asymptotics. So we can see here that the exponential term is determined by the contributing point. And then you have this infinite expansion that depends on these constants, which we can compute. So if you're interested, this is what the leading term looks like. And there are higher order terms, but I don't think it's worth like putting it all on one slide. Okay, so all this is to say is that you don't need to do any of this because you can just run this Sage package that we have. So you can find it, you can install it. It's really easy to install, but you can also find it through GitHub, or we also have official documentation on how to use it. So let's look at more examples of the type of problems that we can solve now using this package. So let's say you wanted to study the binomial coefficients. If you take the all ones direction of the binomial coefficients, you get the central binomial coefficients, and then when you ask it to then compute the diagonal of this, it defaults to the all ones diagonal. It gives you this expansion, which then tells you what the asymptotics of the central binomial coefficients are. And if you wanted to, you can also make it more precise by again asking it to increase the precision. So now it gives you 3 expansion terms rather than just the leading term. So an application that we actually an application of multivariate generating functions comes from molecular biology. So maybe you're interested in a number of ways that strings, so like maybe like DNA sequences, for example, may change over time. One particular such sequence that was studied by Pimentel and Wilson was this bivariate generating function. And now our program can just compute it automatically. Again, so here, these are stored as algebraic numbers, this like long string of decimals with a question mark at the end. But I think in this case, these are like degree 5 and up algebraic numbers. So I don't think they'll have a nice radical expression, but they're still in a sense exact. Okay, so the last example that I teased out earlier is this horizontally convex polyominoes, which is just tilings, you're tiling a grid with these cells such that they're fully connected, and each row is fully connected. So each row doesn't have any gaps. So here again, we're tracking by the number of cells that we have, as well as the number of rows. So in this case, we have like 7 cells in 3 rows. And as you would guess, our package can compute this for you automatically. Asterisk, given that this direction, the direction you choose has n greater than k. So what happens when n is, first of all, when n is less than k, this problem doesn't even make sense because you can't have any tilings where you have more rows than cells. When n is equal to k, then your sequence is just all ones. But what happens in this code is that what happens with our algorithm is that if you look at the critical points as the ratio of n over k approaches 1, it goes off to infinity, and you get this weird like critical point at infinity situation, which currently our code doesn't handle. But that is to say that there are currently like limitations to our program, which we are working on. So one is that certain assumptions we assume to be generic may not be satisfied. So for example, you might have critical points at infinity. Also, if you have like non-transverse intersections, it turns out there are like really crazy types of varieties you can get. So like the Winnie cusp I showed earlier is one of them, but also you might get something like a cone point here, which we have an asymptotic formula for. It's just we haven't had time to actually implement it yet. And also, just if you don't have a rational generating function, then the critical point system is not going to be a nice system of polynomials, so it's a lot more difficult to computationally analyze. But our next speaker, Tia, will give a more thorough treatment of these types of generating functions. And yeah, so besides computing asymptotics, we have other functionality in our package. For example, you can compute critical points of any rational function. It may not necessarily be able to verify minimality or things like that, but it saves you the hassle of having to do a Winnie stratification and then solving this huge system of equations. You can also compute asymptotics in non-rational directions. So you can choose a direction like root 2, 1, for example. If you're wondering why you might ever need to do that, well, like you might care about like limiting behaviors as you vary the direction. So for example, like certain central limit theorems require like non-rational directions. And then we also added the ability to use msolve and locality 2 to do certain backend computations, which speeds it up by quite a lot. And also, if you just want to, if you want to play around with Winnie stratifications or getting univariate representations of polynomial systems, which are things that we use in the backend, there are now also user-facing functions that you can call to do these things. And then in terms of future work, it's mostly just increasing the robustness of the program, so being able to handle more cases. So one thing is like we can do decompositions of arrangement points. So these are factorizations that aren't necessarily transverse. We can decompose them into transverse intersections and then compute asymptotics of each of them separately. And then lastly, even if you don't have a polynomial factorization, so like maybe you have a figure 8, at the intersection point, it locally looks like the intersection of two curves. So you would be able to factor that over the power series rings, and then you can still compute asymptotics in the same way as you would with polynomials, except that now you're working in power series. Yeah, so that's everything I wanted to talk about today. I wanted to thank my graduate supervisors, Steve and Eric, who isn't here right now. I also wanted to thank Benjamin for helping with deploying this Sage package and also cleaning up my very messy Sage code. Thank you.